In this video, we're going to take a look at the end behavior of algebraic functions. Now, we've been doing that for particular types of algebraic functions. Polynomials and rational functions are examples of algebraic functions. An algebraic function is just one that I can build out of polynomials using any combination of arithmetic and root taking. And that's what we haven't seen before. We've seen combining polynomials using arithmetic. If I divide two polynomials, I get a rational. We haven't seen the introduction of roots. And that's what we have here. So I have here the same algebraic function, 3x minus 1 over root 4x squared minus 2x. We're going to take the limit as x goes to infinity and as x goes to negative infinity. Okay. Now, I'm going to go ahead and tell you that in both cases, we're going to get a finite non-zero number. And that's going to mean that we have a horizontal asymptote. Because if x is going to infinity or negative infinity, and y is approaching a finite number, that gives us a horizontal asymptote. But something interesting is going to happen here. With rational functions, if there's a horizontal asymptote on the left, there's the same horizontal asymptote on the right. Here, the limits we're going to get, and therefore the heights of the two asymptotes, are going to be different. And I wanted to tell you how we can see that. Okay. Now, if I know that I have a horizontal asymptote on both sides, and I've just told you that, okay, I can see that they can't be the same if they are not at 0. Because if I look at this, I can see that as x is going off to infinity, the top of this fraction is going to be positive. Now, I know the bottom is positive because square roots are never negative. The smallest a square root can be is 0. Of course, if this were 0 on the bottom, this would be undefined and not in the domain. But as x gets big enough, we move away from the x values that would make this 0. And so we're going to get something that's positive. So this fraction is going to be a positive over a positive. We're going to get a positive limit. Here, if x is going to negative infinity, the top of this fraction is negative, but the bottom, because it's still this square root, is going to be positive. So I'm going to have a negative over a positive, which will be negative. Now, I point that out just because a lot of students struggle with the signs on things like this. And that just gives you a really quick way of checking. Whatever limit I get here has to be positive if it's not 0. Okay. In theory, it could be 0. It's not going to be. If I get a negative limit here, that's not possible because I can't take the limit of something that's positive and get a result that's negative. Here, I can't take the limit of something that's always negative and get something positive. Okay. So how do we actually go about evaluating these limits? Well, we're going to employ the same basic strategy that we used for rational functions. We just have to modify things to account for the presence of the roots. So I'm going to multiply my function by 1 in the form of, now with rational functions, it was the reciprocal of the biggest power of x in the denominator. Now I have to take into account both the power and the root. So if I look, everything's under a square root, and the biggest power under that root is x squared. So basically, let me write this over here, root x squared is the biggest power root combination that I have in the denominator. So I'm going to multiply this by 1 in the form of 1 over root x squared over 1 over root x squared. That's actually going to be the same step that I take down here. We'll do this one second. Okay. But here, what I would do then is I would distribute that. So we've got the limit as x goes to infinity up 3x over the square root of x squared minus 1 over the square root of x squared, all over the square root of 4x squared minus 2x over the square root of x squared. Okay. Now, a couple of things that are going on. I can see here that this piece is going to go to 0. I don't need to really do any simplifying to be able to do that. But this piece, I can't cancel anything because that x is not under a radical and those x's are. I can't cancel unless everything is outside the radical or everything is inside the radical. So I'm not crazy about having stuff that's not under a root with stuff that's under a root. Here, these guys are under two different roots, but I can use a nice property of square roots on the bottom there. On the bottom, I'm able to use the fact that square roots distribute over division. So I could rewrite that denominator as the square root of 4x squared minus 2x over x squared. I can just write it as one big square root of that division problem. And then on top I've got 3x over root x squared, which I don't like, over 1 minus root x squared. Now on bottom, now all my x's are under the root. I'm going to be able to distribute that division and then cancel my x's. Limit as x goes to infinity. I'm going to just leave the top blank for now because we're going to come back and talk about how we can simplify that. But this becomes the square root of 4x squared over x squared minus 2x over x squared. Okay, that's going to become the limit as x goes to infinity. Now I'm still going to have to figure out what goes on top, but that's going to just become the square root of 4, because I can cancel those x's now, minus 2 over x. So how do I deal with the top? Well, what I want to do is simplify the square root of x squared. Now, a lot of people look at that and they make a mistake. They say the square root of x squared is x, and it is not. Okay. Let's just take a look. This quantity I know is never negative because the square root sign can never spit out a negative result. X can be negative. I'm sure in your mathematical career you have solved an equation for x at some point in your life and gotten a negative number. And you didn't say, well, that's wrong because there was no negative sign in front of the x. Variables are very different from numbers. With variables, I can't tell whether a variable is positive or negative by the presence or absence of a negative sign. With numbers, I can. That's a negative number. I know that because there's a negative sign in it. I don't know whether x is representing a positive or a negative number. So I can't say that it's equal to something that can't be negative. What I need to do is take the absolute value. So the square root of x squared, x could certainly be a negative number. Let's say x was negative 3. Negative 3 squared would be 9. The square root of 9 would be 3. That's not x. We said x was negative 3. That's the absolute value of x. Okay. Now, for the absolute value of x, that basically I can think of as a piecewise function. Let's just think about it. If I had you take the absolute value of 3, you would give me 3. You would say absolute value doesn't change a positive number. It also doesn't change 0. But if I asked you to take the absolute value of negative 3, I hope you would also tell me 3. There, the absolute value does change it. So if I plug in something negative to the absolute value function tells me to take the opposite thing. So the absolute value of x is x if x is bigger than or equal to 0. If I plug in something that isn't negative, the absolute value doesn't change it. But it's the opposite of x if x is negative. A lot of times students don't like that because they say, wait a minute, square roots and absolute values, those can't spit out something negative. This is not something negative. This is the opposite of a negative number. I only use that rule if x is negative. So remember, with variables, the presence or absence of a negative sign does not tell me whether the variable is positive or negative. Okay, excellent. So, if we return to this problem, we want to evaluate this limit. I've simplified the bottom of the fraction, but we've got to simplify the top. Well, if x is going off to infinity, I know that x is going to be a positive number. So if it's positive, the square root of x squared, which is the absolute value of x, is going to be x, because x is positive. So I can say this is 3x over x minus, might as well just say this is 1 over x. And now I can cancel those x's. So that's going to become 3 minus 1 over x. And then we're used to the fact that pieces that have x's in the denominator, if x is going to plus or minus infinity, are going to go to 0. And so this is going to be 3 over root 4, which is just 3 over 2. Okay. So that's the value that I get if I take the limit as x goes to positive infinity. What I'm going to do is stop this video here, come back in the next video, and we'll take a look at the limit as x goes to negative infinity and see what we get.